Hello and welcome. The diagram shows a sketch of a wave pattern over a short period of time. Which description of this wave is correct? Settle down, class. The excitement in the room is palpable. I'll have to mute that away from the audio and the video because YouTube is trying to pay attention. And I know we all get excited about waves, but you guys are just going to have to chill out. I'll wait. All right, that's more like it. Which description of this wave is correct? Nothing about this wave says that it's longitudinal. The only time, and we've talked about sound waves being represented as transverse waves because it's easier to draw. So if it said like the diagram shows the sketch of a sound wave, which is represented by the pattern shown here, then it's like, okay, sound is longitudinal. But if it's drawn as a transverse wave, they don't give us any clue that it's longitudinal. We can sort of discard that as incorrect. The other thing that's incorrect is this, progressive. Like this is a stationary wave, right? A bunch of loops, right? Nodes and antinodes. We can sort of inspect the figure and see that. And so what we have here is a transverse stationary wave. And so our job becomes, is the wavelength 20 or is the wavelength 40? I like visualizing the waves, right? And so here I've got 1 meter. So follow along as I draw the wave. Oh, let's do it in pink ink. So starting at this node, I go up, half a wave, 1 wave, 1.5, 2, 2.5 waves is 1 meter. So visualize what you're working with and turn your thinking into a math problem if you can. So if we divide each side by 2.5, we realize the wavelength is 0.4 meters, which is 40 centimeters, right? 40, 80, 1, right? So choice D is correct for this one. Moving right along to question 29, you can see that we've got a double slit experiment demonstrates interference between 2 coherent sources of light waves. In the diagram, the curved lines represent wave fronts. Let's take a look at this one. So they say a wave front. I might call it a crest. Think about that as like the crest of the wave, right? At which point does complete destructive interference or a minimum occur? Instead of choosing the correct answer, let's find the most incorrect answer. There is one up there. A is the most incorrect because you haven't even given the waves which are diffracted through this barrier here a chance to meet, right? So the waves have to superpose to apply the principle of superposition. Here is just like a single wave. So there's no way that we could have interference where there's only 1 wave. The waves don't really start to interfere until like right here. And so here the crest is touching crest, here the crest is touching crest, here crest touches crest, here crest touches crest. And this pattern would continue. We could put like a detecting screen maybe right here, or we could put it some distance away. And we'd find that all along this sort of midline, the midpoint between these 2 slits, the waves have had to travel the same distance. So their path difference is 0. They're going to be in phase. Crest will meet crest here, and there you're going to see a bright spot, constructive interference. So crest meeting crest is an example of constructive interference. When you have a wave that goes along like this, and another wave that goes along right with it, when crest meets crest, that's going to constructively interfere to a double crest. When trough meets trough, that's going to constructively interfere to a double trough. Both of those are examples of constructive interference. So keeping that in mind, if we consider point D here, point D is pointed between this wave front and that wave front for this wave, and it's between this wave front and this wave front for this wave. So it's a trough for both waves. You have the example here of trough meeting trough, and so you get a constructive interference double trough at point D. Okay, so that's also an example of constructive interference, right? It's not destructive interference, it's not a minima. And so by the process of elimination, we can deduce that the correct answer is C. And if we consider that point, we see that there's a wave front or a crest from this wave source, but it's between this wave front and this wave front from this wave source. And so it's a trough from this wave meeting a crest from this wave. And so that's the situation where you've got a wave like this and another wave that sort of matches up to it like this, where crest meets trough, trough meets crest, and that's the destructive interference. That's what's going to cancel the wave out and lead to a minima. And so choice C is the correct answer because it's the one where we're at the crest of one wave, but between the two crests or at the trough of another wave. There's your destructive interference. I really like question 29. That's a good one to sort of think your way through interference there, and also to study the double slit experiment. If you like that calculation too, it wasn't even really a calculation, more conceptual, but if you like that one too, go ahead and leave it down in the comments below. And this has been another worked example with Dr. Schleif. We'll see you next time for one more waves question for today.